Okay, now the program, I want to first point out the members of our team. First of all, the program lists Lars Hansen at the University of Chicago as the PI. There's been a change there. Lars has a PhD in economics and a Nobel Prize in economics, but he's not very useful on computation, so he's been replaced by Young Yang Kai, who's at Ohio State University. He's now the PI on the project. The team members includes me, and my main affiliation is Hoover. I'm also somewhat affiliated with Penn State. Simon Scheidegger, who's a postdoc of mine at Hoover in back of the room there. He has a PhD in computational astrophysics. Carlos Rangel, also back of the room, is postdoc for me, or no, RA for me this year. Buzz Brock at UW, Tom Hurdle, and TJ Kennan. So these are the people that are working on various aspects of what we're doing. And the main objective of this effort is to bring serious computational methods to economics. That's the main objective. But to get funding, we said, hey, we can apply this to climate change policies in particular. So here's the question. What should be the policy response to global warming? And also, in the face of the uncertainties. See, we don't know what's going to happen in terms of the economy in the future. We don't know exactly what's going to happen in terms of climate. There's a lot of uncertainty in the world. Now, the typical models used in climate change analysis are deterministic in that they perfectly understand everything about the economy and the climate and can make perfect predictions. There's no uncertainty. They assume that, for example, everybody knows the stock market prices into the infinite future. They also tend to be myopic in that, for example, in these models, most of these models, if you announce today that we're going to have a $500 a ton tax on carbon, nope, but it's going to be in 10 years, nobody would do anything today. There would be no response today because it's like you think myopically. You make decisions such as how many coal-fired power plants you make, assuming that nothing changes. So that's the advantage of that is that it makes the mathematics of your problem an initial value problem. But now what we're going to be doing is talking about incorporating ideas of where people think about the future, make decisions about what they expect is going to happen in the future. That changes the math to more like a two-point boundary value problem. Also, the physics is not really very good. In a couple models in particular, DICE 2007 and the Interagency Working Group. By the way, this DICE model is like the benchmark policy analysis thing that it's sort of it's where a lot of this policy analysis starts. It's a simple model, but it's one that everybody knows it's wrong, but it's one that everybody starts with. Now, and in that, you look at the equations. Don't look at the book, look at the equations in the code. And you find out that in the numerical code, that this study assumes that CO2 emitted 10 years from now will start warming the planet now. So, it's what we call time-traveling CO2. And by the way, the IWG study makes the same mistake. And by the way, when the United States government says, oh, our studies, this study is what they're referring to, says that the carbon tax should be $35 a ton, this is the physics behind that. So this is what you're getting for your tax dollars. That's the physics. By the way, also, the time resolution in many of these models is 10 years. 10 years of time resolution. It's like, okay, for the next 10 years, what happens today is exactly going to be what happens over the course of the next 10 years. And then 10 years from now, then things change, climate-wise. So that's the nature of the basic integrated assessment modeling literature. What we do is we look at models where there's uncertainty in the climate, in the economy. We also don't know about parameter uncertainty, and we also, our time resolution, I think in the stuff I'm going to show you, was 1 year over like a 300-year horizon, but we've gotten it down to like 1 month for time resolution. Now, the context of this is that economics is stuck in the Stone Age. Stone meaning laptops. So here's a really scary part. You look at the models that the Federal Reserve uses to make their decisions about money supply and financial regulations and interest rates. These are all, first of all, linear. They run on laptops in a few minutes. That tells you something about just how comprehensive they can be. Their temporal resolution is 3 months. Now, I recall the fall of 2008. Things seem to be happening at a pace more rapid than once every 3 months. It was like once every 3 days, another investment bank was in trouble. But no, the Federal Reserve says, no, we're going to have a temporal resolution of 3 months. I looked at the code. The guy who wrote the code for the main model doesn't know about LU decomposition to solve linear equations. He just says, let's invert a matrix. Doesn't know about automatic differentiation. Now, the code in these models is written largely in MATLAB and eViews. You guys don't know about eViews. Good reason. It's something inferior to MATLAB. I asked them why they use eViews. This allows you to solve the problem and graph the results in one program. Okay, this is the level of economic analysis in the Federal Reserve. And I'm not talking about just some schmucks at the bottom. I know the guys in the Federal Reserve economists. I know several of them at the top. Some of them took course from me in numerical methods. One of those guys is actually the Federal Reserve, president of the Federal Reserve of San Francisco. So, and they have no interest in doing better. That's the nature of economics today. As a journal editor once said, when I tried to explain something I was doing, said, Ken, it's nice to write papers for smart people, but that's not what the readers and referees of this economics journal wants. Okay, that's the environment I'm coming from. Okay? But now, despite that, we're going ahead and applying modern tools to these economic issues. And I think I also, So we're going to add uncertainty. Now, here's for those of you who know something about the climate policy literature, you may be surprised if I say that they ignore uncertainty. No, here's the thing to think about. Consider Brownian motion. Now, a Brownian motion, let's say like a little dust particle on the surface of water. Brownian motion, this little particle, dust part, whatever, is bouncing around. Now, the Brownian process has a drift, and it also has a variance. Those are parameters of the Brownian motion process. However, you still cannot perfectly predict the future position of any particle that's following that Brownian motion because there's some intrinsic stochasticity. Now, in the climate policy literature, there is a lot of attention paid to uncertainty about parameters, drift, and by the way, zero variance, but there's some uncertainty about the parameters. But they do not look at intrinsic stochasticity, the fact that the agents in the model really don't have perfect knowledge about the future. Economic productivity, in particular, follows a Brownian motion, and it's nearly a random walk. We incorporate that into our work. Now, here's sort of a picture of what we have. It's a dice model for those basically extended. And what happens is you have the economy. It sends out CO2 emissions into the atmosphere. And then some of that diffuses into the upper ocean. Some then disappears into the deep ocean. But the atmosphere, the CO2 in the atmosphere will affect the temperature in the atmosphere and the temperature in the ocean. And then what that's going to do is damage the economy. For example, if the sea level rises by 30 feet, then I think a good portion of Florida disappears. But now the process by which there's damage is stochastic. It's like, well, we see these glaciers melting, but we don't know for sure when they're going to collapse or fall, or the rate of progress of these things melting. And also, we don't know about the economy perfectly. So we all put that into we put all those kinds of uncertainties into one dynamic optimization model in order to find what the optimal policies are. Now, this basically is, if you don't know any economics, this is all Greek to you, particularly the Greek letters, but the rest of it is also. However, this is just multidimensional stochastic optimal control. This is like if you were trying to control something that was following a Brownian motion. This is this is just Hamilton, Jacobi, Bellman partial differential equations. That's what this is. Now, by the way, what's different about this relative to stuff you may see in engineering is that we have like 10 dimensions, and those are the small models. Other stuff I'm working on with Simon in particular, we have hundreds of dimensions. So how can we handle such high dimensional problems? The thing is that even though this is like a nonlinear partial differential equation, it's diffusion dominated if you're thinking in terms of parabolic equations. Also, the solutions, the functions that solve this are smooth functions. So we can bring sort of high quality pseudospectral approximation methods to bear on this even for our high dimensional functions. So our challenge isn't so much in, like the first speaker today, the turbulence, because that's hard to do because that's the nature of those equations. We don't have that those kinds of issues in the mathematics because it's more like a heat equation. What we have is high dimensionality. And then at the bottom of this is a Bellman equation, as we call it, in optimal control. This is straightforward to parallelize. But now there is basically you start with some guess about, there's something called the value function. Same definition as used in optimal control. And if you know the value function at some future, at time t+1, then it's just, you basically just hit that with some, it's a function in a Banach space. You hit it with an operator, and now you get today's value function. And so there is a parallel block in that you have, just like in PDEs when you're doing a differencing system, and you go backwards in time, then you've got to, you have a parallel block. But the problems are big enough and everything else is easy enough that we get very good scaling. These problems are not small. One example took 84,000 cores on blue waters, took 8 hours. This is not something that those economists at the Fed can do on their laptop, even if they all used all their laptops together simultaneously. So what should that carbon tax be? Well, now the thing is that in this, we have behind here an objective, which you may or may not agree with, but it's a canonical objective in this literature. And so the red line, the deterministic, this is the typical analysis in the climate literature, particularly Nordhaus, is the red line that says that, that carbon tax today should be, ours is above $100, but he would, because he doesn't have the features we have, he has less than that. But this is, the red line is what the canonical models would say should be the progression of the carbon tax, and that does hit our median 50%. But the thing is that because of the uncertainties in the economy, because if the economy grows rapidly, then it's going to also spit out a lot of CO2, and that's going to cause even more warming. You don't know that. So what happens is that the optimal policy is itself a random process, and notice that the 95%, let's say the 90% quantile has the 2100 carbon tax being, what is that, like over $900. Whereas a typical analysis would just say it can't go above 800. So the range of likely values, and the fact that you have to respond to it. You can't just pass a law that says this is a schedule over time. That's not, you have to respond to events. Now, some people say that we should have a 2-degree target. We should make sure that the climate the temperature in the atmosphere never goes above 2 degrees. Well, we can put that constraint in. And now with a stochastic system, let's say you put it in so that you have 82% chance of success. So notice at what happens. This is if you don't have a specific target. This is a 2-degree target with 80% chance of success. And notice all of the carbon taxes go up. And substantially. And then if you want 100%, then it goes up much greater. And in particular, notice the deterministic analysis says that this is the red line on the deterministic analysis. Notice that it basically undershoots what our stochastic analysis is for pretty much any year past 2060. So it is a consistent big downward bias towards what our stochastic analysis says, that if you want to avoid 2 degrees, what you have to do. Now, here's next one. Okay, what's the range of possible warming? Well, here's the IPCC people. They create what they call representative concentration profiles. So like the bad case where nobody does anything is represented by RCP 8.5. That's this line. That's what you look in the IPCC kind of style, and they say, well, that's the bad case. Well, the thing is that they don't take into account economic uncertainty. They just kind of like look at the average case, and they've got like the median case about right, because that's about tracks our 50% quantile. But the thing about this issue is that getting things right on average is not good enough. The loss function is very convex in that it's not that you want to have on average in expectation a temperature, let's say about whatever this is, 4 degrees, 4.5 degrees. No. You care much more about the temperature getting above there than in terms of the temperature being below. You care about the upper tails. The upper tail is the focus. And the IPCC approach grossly misses the upper tail. Now, so we're working on various extensions of this. And we've gotten publications, Nature Climate Change, an Economics Journal, and also PNAS as well. These are the major papers closely related to this. Other papers also had come out on this. And so, this just gives you, talk about impact. The White House, the previous White House, in 2014 actually cited our work as supportive of its case that the cost of delaying action is high, and so we like to quote that. Now, Blue Waters has been essential for this. Now, when I first started this, I had an affiliation with the University of Chicago and also worked with people at Argonne Labs on some stuff. The DOE, however, told me we would not allow economics studies on DOE computers. So because this was economics, it was banned from DOE computers. So then this came along. We put in an application in November 2012, I think was our first one. This is, I think we're starting our fourth. So basically, this stuff cannot be done on laptops. It cannot be done on clusters at a university. I'm at Stanford University. I have access to very little in terms of, like, say, publicly available. It's like a private university. Maybe the computer science department has a great computer system. But the public resources are very poor. So Blue Waters was absolutely the only place we could go for support on this. So then this is also related to an NSF. This is in support of an NSF project related to supporting the RDCEP project based at Chicago. But that's another story. But basically, Blue Waters was absolutely essential. There was nobody else at that time. I even talked with the head of advanced computing of DOE in the spring of 2012. He says, no, that's not allowed. Economics is not science. So the thing is that the Federal Reserve and DOE several years ago sort of had the same attitude. Economics is not science, we don't use the modern tools. I have a different attitude, and I think this is an example of where we can do this. And by the way, the tools that I have here, we're developing, are robust and can be applied to many problems. And one thing we're working on is, is there any social benefit from having derivatives? The 2008 collapse a lot of it was because people were gambling with derivatives and options of various sorts, complex derivatives. And that didn't go well. So what we're asking the question, maybe we should just ban them. And so far the analysis says, yeah, they're more trouble than they're worth. So that's another kind of disaster kind of issue that we can examine with these tools. Thank you.